Hey, everybody! How are you all guys doing? Welcome to the Whimper Podcast, where we talk about all the goofy stuff related to space, astronomy, deep tech, AI, and a lot more to learn about which you won't find much in a conventional form of education. Today, we have a guest who is a part of a relatively new organization that recently launched a payload in the orbit, comprising of a space weather monitor whose name in short is ROBI, via the PSLV C-53 rocket designed by ISRO. He is a working professional who recently graduated from IIST pursuing a BTech in Aerospace, Aeronautical, and Astronautical engineering. And if you're a person who is interested in talking about physics, space, and astronomy in a highly intense manner, you are going to love this one. Our today's guest is Mr. Ananthu Krishna. Welcome to the third episode of the Whimper Podcast. Hope you enjoy it. Okay. Hey everybody. We have Ananthu here on the podcast. And we have hi Ananthu. How are you doing?
Hi, I'm doing fine. Thanks, Divyans, for having me over. I'm excited.
Excited. I'm excited too. Okay. We have two guests over here today. It's Ananthu Krishna, who is an engineer and he's a rocket scientist, and he basically works at Digantara right now. As what do you work like? What is the whole what do you call it? The theme of your job?
So basically, I am a system engineer. I wear a lot of hats at work, but so I kind of do a lot of things. But basically, majority of my job involves mission design and astrodynamics. So what that means is that I design orbits, I design constellations, and basically the system level design of a space mission in order to achieve a certain goal.
Hmm. Yeah, but a lot of technical terms I don't understand. But anyways, uh, we have my cousin brother here. I don't know why he's muted yet. Yeah, but anyways, okay, we'll be starting off with our guest questions. So as we have seen, there are a lot of rocket engines around in the industry, right? Like for example, there are rocket engines which work on ion propulsion, or the most commonly used are basically chemical propulsion ones, right? Which which work on combustion. So, like there have been so many rocket engines around, but why is that only one typical bell-shaped rocket cup used in almost every rocket since the starting of the industry?
Well, that has to do with what you call as compressible flow. So, in order to the whole goal of the rocket engine is to maximize the velocity with which the combusted propellants have to come up. Right. So the way you can do that is by increasing the velocity. Uh, you know, uh, there is something called as having the right area ratio, so that the propellants get accelerated to as much speed as possible. So in a bell-shaped, exhaust, and that's how they have figured out basically optimized it such that that shape gives you the maximum velocity of exit. So when you have that much velocity, you're sending out that much momentum outwards, right? So you get the maximum propulsion forward. So that bell shape basically helps in increasing that momentum.
But then there were also models which with inverse bell-shaped engines, right? Which were less maneuverable, but they were more efficient. Like what I don't remember the exact term, but it was like in this shape, something like that. If you remember.
You mean, okay, a reverse cone kind of system?
Yes. It was it was like the bell shape, the 2D model of a bell shaped has been like the bell shaped is, if it is like this, then it has become like the whole two sides have come opposite to each other, and I mean that is why that is the yeah. I don't
Okay, that's
remember the
actually
exact.
rather interesting because I am not aware of it, and I'm actually not into the propulsion side of thing that
Yes, that's true.
gas
That's
turbines
true.
and stuff. But
Yes.
that's actually rather interesting. I would like to look into it.
Mm. Okay, the type of engine that I was talking about is called an aerospike engine. Now, those of you who do not know how an Aerospike engine looks, I've put a Google Drive link down in the description. You can check out the images that I've taken up from the internet and see what an Aerospike engine looks like. Moving on, talking about payloads, because that's the part that you work with at Digantara, right? Yes.
Yes, payload is not exactly
But satellite.
part of it, but yeah,
Yes,
yes.
yes. I mean, yeah, payload contains a lot of things. The fairing, that's the part because that's going to be on the
So
top.
when you say payload, but there's a thing here. Okay, so
Mhm.
in the sense of a rocket, when you're talking about a rocket, the payload of the rocket is the entire satellite, right? But when you're talking about a satellite, the payload inside the satellite is the main sensor or component that you want to launch into space. So when what Gigantara is doing, we are not in the business of rockets, neither are we in the business of satellites, because satellites is it's a whole different rocket science that we don't want to get into. So what we are doing is we are just building the payload inside the satellite. So the payload, whatever we need, which is like tracking objects or monitoring space weather, we just build that payload and we just put it into satellite from from our partners. So that's what I mean when we say that we are working on payloads only.
Okay. Yeah. So,
A question.
yes, yes,
Sure,
yes.
sure.
So,
So right now, I know your firm is like dealing primarily in like the components inside the satellite, but then you also happen to specialize in space mission designs, right?
Right. So the thing is that I am not the one involved in the payload design. I am mostly in the mission design only. So we have a separate payload team that works on the payload.
So right now, from what I understand, there will be complex trajectory planning that would be there in space mission designs, a lot of mathematics. Do you
Right.
think, what is your opinion? Do you think if we have those futuristic propulsion systems like the one that NASA is propagating, wherein we just bend the space-time uh, and just travel within a second from one point to another, wherein we don't use the conventional rockets? And if that is achieved, then do you think space mission design as such would become quite irrelevant?
by the way, if you want to check out the audio versions of this podcast, you could check out any of these platforms, whether it be Spotify, Radio Public. We are going to be verified on Amazon Music pretty soon too, and Google Podcasts, Stitcher, or whichever one you may feel comfortable with. Feel free to check out our other episodes and follow us on social media, but that too only if you're committed. This is astrophysics, right? I think it is astrophysics.
A very interesting question. I like that question.
Yeah.
It's like if you want to get from point A to point B, you just warp the space from point A and point B so that you get there. But again, that I don't know if that will make mission design irrelevant, because you again still have to do some kind of a math, some kind of calculation.
So
But yeah,
is he talking about wormholes? Are you talking about wormholes?
wormhole, I think, would be like a higher level version of what he's talking. He's warping the space time essentially, right? You can
So
warp it.
if you're technically talking about warping this space time to a certainty where 2 points could meet each other, that's like that's like a lot of gravity required around it, right?
Yeah, yeah.
Like almost a black hole beneath him.
Amount of effort.
Yes, yes,
But I don't know how practical that is. But
yes, yes.
for me, it's still science fiction.
Yeah.
Yeah, sure it is, but that NASA is carrying out experiments. So I was just wondering if that happens, if it goes through, that they just perhaps become irrelevant. Like so much of math would be avoided then.
No. But again, if you're warping space time, I think that will only increase the math. You'll have like a whole different level of four dimensional math to solve, I guess.
Okay. Do you want to continue or shall I continue? Okay, I'll do that. Okay. Talking about payloads in which satellites, when getting into force, mainly seem to use ion propulsion engines. I think most satellites use ion propulsion engines. I don't know. But
Small satellites use, prefer to use ion propulsion because
yes,
it's smaller. You can fit it into two sets.
so through which they can attain higher speeds but yet lower acceleration, because ion propulsion engines have really low accelerations, right? As to what I heard, that one of NASA's satellites was unable to completely slow down itself by about 94 kilometers an hour, and it took it around 4 days to do that. So that was a really long amount of time to just decelerate an object. So, have you been familiar with ion propulsion?
I mean, I'm aware of ion propulsion. I know why it's preferred in small satellites. The thing is, ion propulsions, although their thrust is very small, the advantage that they give is that their specific impulse is very high. Now, what that means is that for a given amount of fuel, ion propulsion gives you more energy than chemical.
Yes. As to what I heard, I think in comparison to combustion fuel engines give around 3.5 kilometers a second, and ion propulsion engines give around 40 kilometers per second, which is like even greater than 10 times, right? So,
Okay, what are those numbers? It sounds like delta V's. Right. Change.
no, this is uniform velocity. It's not acceleration I'm talking about. Because if I told to have been the acceleration, I would talk about kilometers per second square. It's kilometers per second.
Yes.
Yep, continue.
Yeah, so to get like the same amount of delta V, a change in speed, the ion propulsion will take a longer time than chemical propulsion. That is the only difference there. And of course, the amount of fuel or the amount of energy taken by the ion propulsion will be lower. But yeah, that's a compromise that you make.
Okay. Why I brought up ion propulsion is because I got familiar with one of these concepts. I mean, it's completely hypothetical. I don't know even if it's practical, but I just thought about it. In fact, I drew a model of it. But anyways, if you want me to show it, I will show it accordingly. But yeah, one of the concepts that I thought I'd be talking about was that dual engine method of using rocket engines, which was like, what if we take a rocket's first stage, basically comprising it of we could say hydraulic systems, to timely shift the engines according to their needs. For example, if it is difficult for me or for any organizations to decelerate an ion propulsion rocket engine, we could just cut off the power, right? For example, if like, let me elaborate. If like during a launch, I need a really high acceleration against the gravity and the drag that is going to be there. So I would need combustion engines in that case, but definitely. But when the rocket gets into orbit, after that, high acceleration becomes sort of irrelevant at some points, because if the rocket has to go out of the orbit, like it has to go from apogee to perigee and change its apogee and perigee all the time, the way it was done in Mission Mangal, as to what I've seen. So unless the case is like that, I think I would need combustion engines. But when the rocket gets into orbit after that, and high uniform velocity is required in that case, and at least in the orbit, high uniform velocity is required. The rocket or the satellite has to move at a certain uniform velocity all the time. It does not have to accelerate or decelerate, right? So basically, that part could use ion propulsion. And then now in this case, that we can switch engines by attaching them to hydraulic hands, or the way you've seen in cranes and JPGs. So I want to know, like, what's your thought on this very idea? Like, let me show you in fact the diagram too, if you want me to do that.
No, let me give you my thoughts first. There's a thing that you don't send an entire rocket as it is to space. So rockets have stages, right? As soon as it reaches a certain altitude, it drops the first stage, and then it goes up higher and it drops the second stage. So you don't technically need switching between engines. You can just put these chemical propulsion for all the lower stages, and the upper stage that actually takes the satellite to the velocity that it needs to go. That can be an ion propulsion. So you don't need to have two separate systems that are obviously heavy on its own and then shifting between the two. You can have the first phase of the trajectory done by chemical propulsion, and then you can drop that onto the earth, and then
That's a typical thing that happens already, right? If the chemical combustion part is done, but then if I take this to even a higher scale, like interplanetary missions, then in that case I would need acceleration, deceleration all the time, almost.
yeah. So
At
I
least
like
because
the idea because so you will have a lot of options in the amount of thrust you can have, but you need to work out the mass budget. Do you have sufficient mass to have two different types of propulsion systems and two different types of fuel maybe? And will it work out for your mission? If it works out for you, it's a really good idea because you can have a low thrust operation, you can have high thrust operations. That's probably
Because hydrogen or oxygen are going to be the ones that are going to occupy the most amount of weight in the first stage, I think. And then xenon is going to be there in the ion propulsion engine. So xenon is basically a noble gas, so I don't think it would be having a lot of relative mass compared to what oxygen and hydrogen would be having. Right. So it's almost going to be negligible in comparison to them. So I don't know. As I said, it's completely blurry. It's just
The thing is that even now satellites use multiple propulsion systems for different things. But there, it's like for linear propulsion, you use one system. For attitude control, you use a different system. Like we may have an ion propulsion system for linear motion, and then you use cold gas thrusters for attitude control, something like that. So you certainly do have options of having multiple propulsion systems. You just need to do the math and figure out if you can.
That is mostly because, unlike conventional computer systems, ion propulsion and all cannot basically give you the lift off. It can only generate the thrust in the space you need for maneuvering. Right?
Yeah, that's what I said. That's what I said. Just cut off the power of the ion propulsion engine when it's not needed. And because we can do that, we do not decelerate it really well, but we can cut off the power. And we can also do that with the chemical propulsion engine as well, because we at least till the moment we don't need high acceleration. For example, why I came with this idea is because if you've heard of this term called Hoffman trajectory, right?
Hoffman transfer.
Yes.
It's a kind of orbital maneuver.
So because we have to wait every 26 months for Mars to be the closest to the Earth, right? So at that time it is at around 64 million kilometers or so, and then when the Mars is, the planet is basically where it moves basically forward, it is around 264 million kilometers, and at least we have to move in a trajectory that we have to predict where Mars is going to be after this much amount of time. I think that's what Hoffman transfer is, right?
I don't know. I don't think that is Hoffman transfer. That's like when you are raising a certain orbit, you just what do you say? You just do impulsive maneuvers to first raise the apogee to the desired orbit, and then you reach the apogee, you raise the perigee to the desired orbit. That's the Hoffman maneuver. So in the Hoffman transfer, you need high impulse burns.
Yes, because we have to get out of Earth's gravitational field too. So in that case, we have to exit the Earth's gravitational field and then reach, and then Mars's gravity would help us assist to get inside it.
Yes.
So that is why I thought about it in this way, because let's take it in 4 stages. The launch part is going to be done with the chemical propulsion engines. Then when the rocket is in the orbit, we don't need any chemical propulsion for acceleration at the moment, so we'll just keep it that way. Then only at certain amounts of time at the same point, like that's how it's done, right? When you power up the rocket, and then its orbit increases, then again it reaches that same point, and then you power it up, and then again the orbit increases, and that's how you just catapult it and out of the Earth's orbit. So that was that is this is the method that is done basically when the budget is low. I don't know. At least that's how they portrayed it in the movie. But if this is a way that it is done still, then probably this would work out. And now the part of the chemical propulsion engine is finished in the Earth's orbit, and when it starts exiting, we do not have, because we do not have to like wait 20 like months, so that the rocket, like 9 months for the rocket to reach Mars, because that's a lot of time, because we have already spent 26 months planning, and now 9 extra months, so that's going to be a lot of travel time if we really want things to be flexible and smooth. So in now shall we start the ion propulsion engines, and then we could get a higher amount of uniform velocity, right? And the maneuvering can be done with the help of jets that are put beside the satellite, and then it would be able to reach Mars in a pretty short amount of probably, I don't know, I haven't done the math. Yes, we can get, I haven't done the maths because I even don't know it, but I'm just saying. So you got to reach there, and then probably cut off the whole power of the ion propulsion engine, reverse the rocket, I mean the satellite, and then start decelerating it, and then probably the Mars orbit will catch us up, and we would be in the Martian
Just
orbit.
that small catch there. If you get there faster, you might be, the amount of acceleration you might be higher.
Will be higher. So that is why I said, if we have two different propulsion engines in the same satellite, then probably this could work out. But
And there
as I
is
said,
the component of cost, obviously, and you work getting there faster. You need to do all that also.
but if we have to, if we have to like build a civilization there, as what they are planning there in the US, but then I think the things need to be a bit more flexible. Like, how would you wait for 35 months? Damn. That's like over 3 years, about 3 years, yeah. So, I mean, that's going to be a really difficult thing to do. Okay, we'll talk about this later, but moving on. So coming on to some questions based on macro-sized organizations. This is not space science, no. I'm just asking about how organizations, specifically, like at which you have worked in, work, and how they basically perform, and what is the work culture like, and all of that stuff. And like, are there different stages, and or are there different rooms or groups of people for different kinds of work? Is it done that way? Because there's one satellite that you have to make, right?
So here you find like a huge difference between how a large organization functions and a small startup function. I have worked for only 2 startups till date. So the thing about startups is that you have a lot of very less people and a lot of work to get done. So one individual will be responsible for a lot more things, right? So you have to wear a lot of hats. You'll have to do a lot of different things. Like for example, I've done not just dynamics. I've done communication. I've done optics. I've done a lot of things, right? But in a big organization, you have teams for each of these tasks. So a certain individual will be responsible for more of a specific task within the entire big picture. So that's one difference between this. And I would also say that maybe in a small startup like culture, you have lot more say in the decision making. There is no hierarchy structure per se, but in a huge organization, you'll have a big head. You have someone above you and then someone above them, and then in order to get some ideas out, to execute some of your ideas, you need so many approvals. You can't make a big difference in that organization, but in a startup you can. That is another major difference.
Okay. One more thing. Have you finished it? Have you finished up with the answer?
I think I would add that in terms of efficiency, maybe I might offend a few people, but big organizations aren't very efficient.
Yes.
But, startups will get things done faster because they have lesser signatures to get, approvals to get. They just get stuff done. That's the difference.
So then probably government intervention slows things down, right? Even in a startup, if government comes in and starts playing its role, then probably things would
Any
start
kind of
slowing down.
authority will slow things down for sure.
So why does that even happen? Like government wants to support space research in itself, but still it does not provide that much of flexibility and smoothness that should be there in the work function, the workflow.
It's like
Why
a
do you
two-sided coin. You cannot avoid having that control over a big organization, right? Because there are so many people and so many things that could go wrong. So in order to get such a big group of people, the big goal, aligned, you sometimes kind of have to have this system in place. So, that will kind of end up in this, negative side of things being slower, but it also has the positive side of the entire organization moving in the right direction. So it's a two-sided coin. It's difficult.
understandable? Okay. Because you are more into predicting the weather conditions and this basically constructing satellites which are able to work on weather conditions of or climatic conditions of places around the planet. Is that something like that?
Yes. So here's the thing: weather, there's a difference between terrestrial weather and space weather. So terrestrial weather is what we usually say, sunny, rainy, the temperature, humidity, and stuff. When you go out into space, the weather means a totally different thing. So although it, both terrestrial and space weather basically originates from the sun, the space weather drivers are different. It's things like charged particles, radiation, uh, things like magnetic field. All of these will affect how a satellite, performs in orbit.
Because okay, because you have to go through
Okay,
the
talking about
yeah, speak.
yeah, like we were discussing about weather, right? So talking about a bit about space weather, it's like quite unpredictable there, right? Like anytime there's a solar glare and all that. So
Yes.
like we were discussing about engine and propulsion, these are things that we can calculate beforehand. But when you're designing a space mission, how do you take into account these solar flares and everything? Is there any way to take that into account beforehand?
So that is one problem that we want to solve. So right now it's very difficult to predict. The sun will, all of a sudden throw a tantrum. SpaceX lost 40 satellites, if you read about it. Well, that happened a while ago when, the sun threw a flare and suddenly the atmospheric density increased and they lost 40 satellites. So right now it's very difficult to predict flares, very difficult to predict coronal mass ejections. So the way we can do that is basically we need to understand the sun and the space weather better. So at the moment, there is very little information about it. There is very little data. So what we want to do is we want to solve that by sending as many sensors, space weather sensors in orbit. So we have real-time data coming in. So when we have lots of data, we'll be able to say something. There is a flare that might come up in a few hours. Please turn off your important systems or do some kind of safety procedures. So that's what we're trying to solve. It's very difficult to predict, but that's a problem that needs to be solved.
Basically, like a tsunami warning system, we just place sensors in the water, just like that.
Correct. So you at the moment, apart from sending satellites to lower orbit, you can also send satellites to what you call as Lagrange one point, L1 point. That is the space between Earth and Sun. So those points will experience the flare or the flux of protons or radiations even before it reaches Earth. So that is one way to do it.
Okay.
Anything else?
Okay.
Okay. Just not just space weather conditions, but even predicting the weather conditions here on Earth is quite difficult for a satellite, right? Like you can't, yeah, I know can't be guaranteed about it.
Forecasts are.
Yes.
Because
So
it's like
not only about weather, I think there's some particular impact about albedo of the Earth, an impact from the air glow and Earth geomagnetic field effects also on space mission design. Can you like delve into that also a bit further?
okay, when you talk about albedo, that will affect things like Earth observation missions. So Earth observation that, looking at Earth, imaging through either visible light or infrared light. When there is a higher albedo, it will increase the noise in your image. So that can be unpredictable. And, magnetic field variations will basically suddenly change the amount of protons that will hit your satellite. So these things can affect the electronics on board. So, all of a sudden your, program might stop working, you might have to restart, things like that. And this magnetic field, one manifestation of that you can see is the aurora. You might have seen photos, or at least, I don't know if you have seen it for real, but that happens because of sudden variation in magnetic field. So, and how this aurora works is because of the sudden flux of charged particles. They come and hit the atmosphere and they react.
The ones that happen in Arctic.
Yes, exactly. The one that it actually happens on both poles, but there's no one in the South Pole, so nobody sees it.
Yes.
So it just reacts with the atmospheric molecules and gives the emission spectrum. Oxygen gives out green and others give out other colors and things like that. So that is one manifestation, but in space also it affects satellites in the form of radiation, and it will affect your instruments, whatever sensors that you have. It will cause variations in those.
Okay.
And one more thing is that, as I mentioned about SpaceX, when there's a sudden solar flare or influx of, particles, the
Yes.
starts heating up. So things that the satellites that are in lower orbits, they will suddenly increase a higher drag. So that's how SpaceX lost the satellites. When it sensed the higher drag, it went into safe mode and it will come out and just deorbit. So when you put satellites below something like 500 kilometers, this sudden increase in drag can completely spoil your mission. So you need to account for that in mission design.
And this is primarily not for, I guess, not for interplanetary, unless you're exactly talking about the frame wherein they reach there on the planet's orbit. But what is the general strategy for rendezvous in Earth's orbit or that planet's orbit? When you're talking about space mission designs, how do you deal with that aspect? What is the general strategy and the mathematical calculation behind that?
You mean rendezvousing to another satellite? Is that correct?
Yeah.
Okay. I haven't personally worked on rendezvous, but the thing is that first of all, getting near to a satellite is very difficult. So if you are getting near to a satellite, it should be your satellite, because otherwise you wouldn't know accurately where it is. So if it is your satellite, if both the components are yours, you will have an idea about its position. And there are, established maneuvers, just like Hoffman maneuvers. There are maneuvers that you can get closer to an object. And once you reach, there's an interesting part about once you reach closer, close enough to your, object. Let's say you want to dock, then you shift into something else like a LiDAR or a radar to see the object that is near you. Because after that point, it's difficult to, work with GPS coordinates. After a certain point, you just move into LiDAR and see. Then you just try to get closer using those LiDAR information and dock into the, either the ISS or some other satellites. Currently, there are companies that are working on this kind of stuff, in-orbit servicing, in-orbit fueling. All these people are working on the operations right now.
Okay.
So, my next question is that basically predicting the weather conditions of location by the present technology on Earth is still difficult, right?
Yes.
So, something like satellite mapping and weather forecasting, as to what it sounds, seems pretty boring, I think. You have to predict the weather conditions of a place, but how difficult or how big of a problem solver does one have to be to solve the problems to which we still don't have the answer to? Because it sounds something basic, although just predicting the weather conditions of a place, how it is, but it's still, it is not. So yeah.
When you say weather from a layman's point of view, it's just, okay, when is it going to rain? What is the temperature? But when you think in scientific terms, there are so many drivers. First of all, atmosphere is complicated. How the winds, how the air movements are happening at a place is very difficult to predict. And how it carries, moisture from water bodies, how it moves through the terrain, how it sheds that water. It's a very complicated numerical models. Even at the moment, in order to predict weather, you need to have supercomputers crunching numbers all the time. It's a very complicated numerical solution. So from a scientific sense, it is a very complicated problem. That's why it's difficult to do it. It sounds easy, but it isn't. That is the core of vision.
Okay, moving on. So basically, we were talking about LiDAR a couple of days ago, right? So if you could just elaborate for our audience as well, that what is a LiDAR and how accurate is it and in which conditions?
Okay, so LiDAR is basically similar to radar and sonar. And so instead of radio waves or sound, you use light for ranging. So it's an active form of detection, which means that you send out light, and the light reflects off of objects, and you detect that light, the reflected light. So the way it works is that you take the time gap between sending the light and getting the reflected light, and you use that time gap and the speed of velocity, the velocity of light, and then you get the distance. You get the distance of the object. So that can be used to get the accurate position of an object in your field of view. So, I mean, it's very accurate in the sense that the accuracy is, it will be in the order of the wavelength of whatever signal you use. For RF, for radio frequency, they're in the order of centimeters or meters. But light, that the wavelength is like nanometers. So they're pretty accurate. But okay,
But the range would be shorter, right? Like it would be as much as our visible range.
Yes, correct. So the range of photons, it's much shorter. So you need a lot more power in order to, detect something that's very far. That is also correct.
Then probably we are not just working within the visible range of light. So because the speed of light is going to be the same everywhere, the frequency varies.
Yes.
So what
we can even use infrared. So we are working on infrared. I mean, there are multiple reasons for it. One of it is that it's safe for the eye, the frequency that we're working on. So it's safer for ground, while testing and stuff. And I mean, there are a couple of other reasons which I don't want to get into. So you can use any the thing is that the reason why we want to go into LiDAR is because miniaturization. So if you want to miniaturize a radar, it's really difficult because, just like accuracy, the size of the antenna is also dependent on the wavelength. So the amount of, power and the amount of, not power, the size of the devices will be higher for a radar. But for a LiDAR, you can miniaturize it very easily. So you can put these things on CubeSats and send out LiDARs in space.
Okay. But then, what if something because we are using light technically in different frequencies, and especially you said infrared. So, if something blocks the visible light or whatever the light that is being reflected off the surface, and that would be coming to the satellite, if something blocks it, then what do we do in that sort of a condition?
Well, you can't see the object then basically. So, but since you are sending these things out in space, right? And the objective is to detect objects in space. So, I don't see anything blocking the object, but if it is blocking, we want that object. The whole idea is to get the idea of, what objects are there in space, right? So if anything comes in the field of view, we know it. So we want that information. So whatever is blocking, that will also be object, right? So we want to know about it. What is the speed, what is the position, and we get that information.
Talking about not so space weather satellites, the Hubble Space Telescope, which was basically a tenth of the power of what the James Webb Space Telescope is. So why did it take so much of time since then to develop another telescope, and that too just like 10 folds the power of what the Hubble is? What do you think?
Well, complexity is not just in the 10 folds of power. It's also, in the size, in the, in the technology that is used. Also the orbit. Hubble is in Earth orbit, but James Webb is where it's in Lagrange forms. So it's like already very far, and it's doing it in infrared. It needs, advanced cooling systems. The all in all, the complexity of the system, warranted a lot of research, decades of research, billions of funding. The difference is not just in the 10 folds of power. There's a lot more difference than that. That's why.
If I'm talking about a satellite that just sees through the space and at objects that we are targeting at, does a satellite work in a similar format? Like if this James Webb is able to see something that is 13.8 or 13.5 billion light years away, does that work in a similar concept that something has traveled 13.5 billion light years far from where its current location is, and then it's seeing at those objects? Is that the basic concept of how these telescopes work?
Yes, correct. So, right now, when you look into the sky, what you're seeing is not the current time, right? You're seeing what happened like billions of years
Billions of years
on
ago.
the distance, right? So, it's the things that are farther away. You might have heard of, red shifting. The universe is constantly expanding, right? So, the things that are farther away from you are moving faster away from you, right? So, objects that are moving away from you, the colors from it shifts towards the red side. Okay. So things that are moving faster, the colors will shift more towards the red. So things that are moving very fast, it goes way beyond the red color. It goes into infrared, right? So when you're detecting infrared, lights from infrared light coming from stars, what you're seeing is stars that are going very fast away from you. And as I previously said, objects that are farther away from you are moving faster away from you. So what you're
So, like you said, things are moving faster away from you or faster in space time itself. Like because the space is expanding, the things are
the
moving.
thing is that the things are not the space is expanding faster. So that's what this whole idea that things farther from you are moving faster from you is not because the things are moving, it's because the space itself is expanding.
The space is accelerating in its expansion, something like
Yeah,
that.
not exactly accelerating, it's just expanding everywhere. So things
So
that
is it uniform? Is it uniform or is it like is it speeding up? The expansion is speeding up or not?
expansion is, I think, slowing down. I'm not sure though. I don't know how the expansion speed is. The reason why farther things are going faster is not because of change in the speed of expansion. Like if you draw a point, 3 points in on a piece of paper, okay, and if you put 1 point in the center and you zoom that paper, okay, the point nearer to you would have moved a smaller distance than the point farther away from you. So it's simply how expansion of space works.
So that's perspective, right? Because you, the observer, moved somewhat closer and zoomed into the one specific object. The other one moved a bit farther
So
away.
yeah, it's a perspective. So with respect to you, the things that are farther away from you are moving faster. It's purely with respect to you.
Mm-hmm.
It's a thing about perspective in a sense. Yeah.
Mm-hmm. Okay. Moving on. What are the multiple ways a country can use its satellites and its assets in space? This is basic,
Oh,
but yeah.
yeah.
Uh,
I think Google will give you a better answer, but okay,
yeah.
I'll give you things off the top of my head. It can improve, agriculture. One major thing is that Earth observation improves your idea about crops and soil qualities. That's one thing. But moving on to the more interesting side, defense has a lot of use. So you can observe what your enemies are doing. You can secure your borders. You can track where ships are going, things like that.
Hmm. Yeah, but this should not go long. This is a really basic one. So, uh, like, Adibhai, have you seen Pokhran? Hello?
Yeah, me.
Yeah,
Yes,
yeah,
I
yes,
have.
yes, yes, yes. Yeah, yeah, yeah. Even I haven't like I have watched half of it, but I understood the concept of what the technology was in that about which we were talking a couple of days ago. So basically, it was like. So could you recall the part where the cast was talking about two spy US satellites which had a time gap of about an hour in which they had to
Yeah,
test
yeah.
their nuclear missile? Yeah, right. So
Yeah. All the work had to be done at night for 1 hour, and then the buzzer would go off, and then the satellite would come, and they would have to remove all traces of activity that was there.
okay. So did they also like to tell that all those satellites that both of the satellites could observe the time in a person's watch standing here on Earth? Was it something like that?
Yeah. That was the American satellites at that point of time. Yeah.
Uh-huh. So when I asked this the same question to Ananthu the other day, he said that this sounds like science fiction. So that I don't think that some satellite like that exists.
In fact, today, India's local satellite systems can see up to, like, if I'm not wrong, around 20 centimeters above the ground. That's how clear the resolution has become. So of course, Americans, though, they were ahead only.
Okay, I'm not sure that works. 20 centimeters above the ground. Or what exactly does that mean?
In the
Centimeters is
if you're talking about say Aeronautical forest, rainforest, okay.
Okay.
So the average height of the tree there would be in meters, right?
Okay.
So penetrating those things also, it can make up a map of the ground surface with an accuracy of 20
That's possible.
centimeters.
That's very possible.
Like to the mountainous regions, right? So looking at the forest is hard to recognize where there is a small cliff or not, because it's all quite green or white. But the satellites, looking at the ground surface above 20 centimeter accuracy, they can make a height map and everything like that.
So that is that works by penetration of that radio signals. It goes through the trees and it reaches the ground. But here the thing is that it's all about resolution, right? So as you mentioned, 20 centimeters. Usually, Earth observation missions resolutions are in meter. The best I've heard is like 15 centimeters, 30 centimeters. So what that means is that like one pixel will be that big, right? So like think of a watch. A watch is what 2 centimeters, 3 centimeters. In order to see a dial, you will need a millimeter level resolution. At the best of my knowledge, such a technology do not exist right now. So I mean, it honestly sounds to me like a Bollywoodified version of her story. But I would be happy if someone could prove me wrong in this.
Okay. Any like the questions on my side have almost ended. So, anything do you have on your side, anyway?
Okay, to be honest, you spun the topic of discussion so far and wide. Hello.
Yep. Now it's clear.
Hello.
Yep. Now it's clear.
Ah,
So he's looking up questions. In the meantime, I have a question for you. Like, what is the thought process behind naming it the Wimper podcast? It's quite a
Oh yeah. Yep. So basically, we came up with 3 names actually. It was like quick. It was like in 5 minutes. I came up with 3 names. I pissed him, and then I said that, look, I've come with these 3 names. Which one do you like the most? And the 3 names were the Whimper podcast. The other one was the Giant Leap podcast, and the third one was 764 million trillion, which was like completely bizarre. But yeah. So
so this Wimpa thing.
yeah, I know what it means.
Yeah, so that's where my heart said, okay, this is the topic.
Actually, it reminded you of what? That is what he's asking.
It reminded me of me wimping around in some mathematical session, because the person's profile here was like space mission design. The first thing that came to my mind was, okay, this is like a lot of maths, and that's why my first imagination while a question was like, what if we could just bypass it by just making a wormhole?
okay. It looks like someone hits math a lot.
It's the same. It's the same everywhere. Like I hate it, to be honest. I mean, I only like using maths in basically physics, but chemistry is bizarre completely. So
True. So I know you will be heartbroken to see that. Like, from his talk, it would feel like, okay, he's a scientist already.
no, he. In fact, we talked when we talked the other day. He said that he loved physics himself. He was a physics pro, and he was not really great at the other subjects. But yeah, it's the same. Yeah. So yeah. Hey everyone, Thank you for listening to the third episode of the Wimper podcast. Hope you enjoyed it. And this is your host, Divyansh Kunjan, signing off.